All right, afternoon, everyone. My name is Reg Dewitt, and I manage the environmental testing lab for Intertek in Jakarta, Indonesia. And I'm going to talk about physical and chemical impacts of mining. It's a very large topic, actually, so it's going to be challenging to fit it into 15 minutes, but I will try my best. I'm going to talk about the 4 key basic water quality tests that mining companies like to use to monitor their environmental impacts. And then I'm going to zero in on 2 specific chemical impacts. I'm going to talk about the use of cyanide in gold mining, and I'm going to talk about acid rock drainage, or also known as acid mine drainage. This is a very significant impact which many mines face that are unlucky enough to have this particular problem. So, vital signs, the 4 basic water quality parameters. These parameters are followed by mining companies because they want to observe their impacts on the flora and fauna within the water bodies surrounding the mine sites. Many mines are surrounded by water bodies. Mines need a lot of water in which to operate very often. And these photos, you can see staff in the field. They're actually taking these particular measurements. And you might notice that they're holding these field meters, or direct reading meters. These are the instruments that are used to take these 4 particular measurements. And these have to be done in the field, because if you were to take...
Hello. I reckon we've got a technical problem with that one, so rather than having the clicking noise, I'm getting the guys to turn that off and handing you the microphone of power.
Okay, cool. All right, cool. Okay. So, yeah, they're holding field meters. And now, if you were to take these samples of water and send it to a laboratory, by the time the samples arrived at the lab, the readings would change. So it's very important to take these measurements directly in the field. The first measurement that is often taken is salinity, or electric conductivity. If you look at the bottom, you'll see that conductivity is actually comprised, it's the sum of all the positive and negative ions in a water sample. So calcium, magnesium, sodium, potassium, but also the negative species, chloride, sulfate, and your carbonates. Now, the reason why we test conductivity is because aquatic species actually have a particular comfort zone. And so, as the analogy I will give, imagine taking a seawater fish and throwing it into a freshwater lake. It would die right away. And vice versa. If you took a fish from a lake and you threw it into the ocean, it would also die very quickly. Aquatic species need a very specific comfort zone. And so, salinity and conductivity become very important. The next measurement, which actually relates with acid rock drainage that I mentioned earlier, is pH. And the same thing, aquatic species have a certain comfort range for pH. It tends to be a neutral pH. So it'd be a pH from 5 to about 8. And if the pH deviates out of that range, you'll have serious impacts on your aquatic species. Acid rock drainage will cause, of course, the pH to drop in your waterways. Another reading that's taken often at mine sites is dissolved oxygen, and some mine managers actually ask about that. Why is it necessary to measure dissolved oxygen in my waterways? But if you think about it, these mines are crushing a lot of rock. The rock contains minerals, of course, and some of these minerals will actually oxidize. For example, iron. Iron easily oxidizes into rust, and a lot of this rock will often have iron in it. As your iron is getting oxidized, it's actually pulling oxygen out of the water. And natural bubbling river water has a dissolved oxygen of about 8 parts per million. But as you pull oxygen out of the water and the dissolved oxygen begins to drop, when it hits about 3 parts per million, that's when your aquatic species start to actually suffocate. There's not enough oxygen in the water. So many governments will actually set 3 parts per million as a regulatory limit for dissolved oxygen. It's a very important parameter. And lastly, turbidity, also one of the most important measurements taken at mine sites in the waterways. So suspended particles will diffuse sunlight, and that means that the sunlight is not getting down deep into the water body. That causes photosynthesis to be reduced. And it's photosynthesis that generates food for aquatic species. So a very dramatic impact. But not just that, suspended particulate also clogs fish gills, and it also smothers fish eggs and benthic insects, which are also very, very important for the health of an aquatic ecosystem. So now for more specific examples, I mentioned I'm going to talk about the use of cyanide in gold mining, and maybe not many of you knew this, but cyanide has been used in gold mining for more than 130 years. Yeah, it's an old technique, but it's still used to this day. And the reason why gold mines use cyanide is, so they actually crush their ore and they mix it with a dilute solution of cyanide. This allows the cyanide to bind to the gold in the ore very strongly. But the problem is the gold mines, they have another problem. The cyanide doesn't just bind to gold, it also binds to all the other metals in the crushed rock, including toxic metals. And the mining company likes to use the lab to help them quantify this problem, the complex species, of the cyanometallic complex species. So if you look at the illustration here, you can see that, so imagine instead of a sand mine, you've got a gold mine there, and near a river, and no matter how hard the gold mine tries, eventually at some point it can happen that these cyanometallic species will get into the water. It's very difficult to have zero tolerance for this. It can happen. Now you imagine the metallocyanide complex is drifting downriver, and then further down the river they get hit with sunlight, intense sunlight. The ultraviolet radiation from the sun can actually break some of these bonds, the weak bonds, the weak cyanometallic bonds. And it's these species that we try and quantify for the gold mine. We help the gold mine. So if you look at the table on the left, you can see a whole bunch of different examples of metallocyanic species. And on the right side of the table, you'll see the strength of their bonds. So the strongly bound cyanometallic species are not a concern for the gold mine because they're actually quite inert in the environment. They don't react with anything. But the problem happens with the weaker bound cyanide. So for example, the bottom, zinc cyanide and cadmium cyanide are weak species. These are the ones that are more likely to break. And when these species break, you'll have a separate metallic ion, could be even toxic, and you have a free cyanide. When cyanide is in its free form, that is when it's very dangerous, when it's very toxic. That's when it kills. So in that river example, downstream, kilometers downstream, you can get a fish kill event. And the gold mines absolutely want to avoid this from happening, of course. So the test we do in the lab is called WAD, or weak acid dissociable cyanide. And if you look at the top left picture, that's the old way we would do it. So we actually cook a sample of wastewater from the gold mine for them. On the left, you'll see a vessel that adds an acid to this reaction. Now, we want to break the weak bond, because that's the toxic type of cyanide. So we'll actually use a weak acid. And the weak acid we use is acetic acid, or vinegar, for lack of a better word. Now we cook it with this vinegar, acetic acid, and then the free cyanide will then drift across to the right in a trapping solution, an alkaline trapping solution. And it's this trapping solution that we add a reagent to develop a color. If you look at the bottom diagram, you'll see color intensity. The more cyanide in the sample, the more intense the color. And we use a spectrophotometer to accurately measure this cyanide content. Nowadays, we miniaturize everything. So on the right, you'll see we don't just get one sample from a mine, we'll get many. So we can actually pack 50 water samples into a hot block and digest them all at the same time with 50 separate trapping solutions. The other problem that mines can face, and many mines face this problem, is acid rock drainage, or also known as acid mine drainage. If the mine is very unlucky, it'll have sulfur in its rock, and that happens a lot. And not just any sulfur, but reduced sulfur. And so imagine for a moment, you're digging up this rock from deep under the ground, and you're crushing it, and it's reacting with the natural elements. Huh? It hasn't seen the light of day in millions of years, so it's very possible for reactions to occur. And the rock that is of concern to these mines is often pyrite or iron sulfide, also known as fool's gold, by the way. Fool's gold is found in many, many types of rock. And if you look at the chemical reaction at the bottom, this is what's actually happening. So your iron sulfide on the left is reacting with oxygen from the air and water, H2O, from your rain. And on the right, your result is iron hydroxide and H2SO4. H2SO4 is sulfuric acid, and this is the problem for these mines, the generation of sulfuric acid. So to help the mine, we try and quantify, we try and categorize their rock for them. They want to know, is this rock bad rock or is it good rock? And we do 2 screening tests. The first one we do is we try and determine the amount of acid being generated from this rock. And on the second screening test, we'll actually measure the amount of sulfur inside the rock. So we'll end up with 2 separate data points. And these 2 data points will help us to categorize this rock for the mine. The first test is called net acid generation, or NAG, and you'll see on the bottom left, our technician is adding some hydrogen peroxide to some of this crushed rock. That is to get it to react. And she puts it on a hot plate, and she'll cook it for a couple of hours, and then she'll let it cool overnight. And on the right photograph, the next morning, she is titrating it. So she's actually measuring the amount of acid that's been generated. But for the screening test, she just wants to know the pH of this final reaction solution. It's called the NAG pH. That's your first data point. And on the next test, we're actually determining the sulfur content of the rock. So in this case, we use a LICO instrument. And on the right side, you'll see our technician. That instrument, by the way, is more than 30 years old, and it's still very reliable. He's inserting a crucible filled with this powdered rock inside an electric furnace at 1,350 degrees centigrade. And at the same time, pure oxygen is being sprayed onto the sample. In this condition, the sulfur inside the rock gets converted to sulfur dioxide gas. And it's this sulfur dioxide gas that we measure through an infrared detector. So that will give us a very accurate reading of the primary sulfur content of this rock. So, and then, by the way, on the left is the modern version of this LICO instrument. And you can see it's only a couple of years old, and it has a robotic arm, so it actually inserts the crucibles by itself and pulls them up by itself. You don't need the technician anymore. Now, we have 2 data points finally, and we're trying to screen this rock. We're trying to categorize the rock. So it's on a classic XY axis, right? One axis is your NAG pH, your final pH of the solution. And on the other axis at the bottom is NAP, or net acid production potential. That's a calculation that comes from your sulfur content from the LICO instrument. So we plot the 2 data points on an XY axis. And if the plot falls in the upper left quadrant, the rock gets labeled as NAF, or non-acid forming. And that makes the mine, of course, very happy. That's good rock. They don't have a problem. But if the data falls in the bottom right quadrant, their rock sample gets labeled as PAF, or potential acid forming. And that makes the mine very unhappy, of course. That's a problem rock. But on occasion, the data will fall into the other quadrants, UC, or uncertain. And that actually makes us very happy, the laboratory, because we have to do all kinds of additional testing for the mine in order to determine if that rock is finally NAF or if it's PAF. And that, in a nutshell, is examples of some of the tests that we perform for the mines so that they can help monitor the impacts they have to the environment. And I hope you learned something today. And with that, I thank you. And please come on to booth 29 if you have any questions.